So it turns out that I could actually boil this entire chapter down to one page. And that's actually what I tried to do earlier this semester. I spent a lot of time just tearing apart this chapter and thinking, what's the shortest way that I can teach it? I got everything on one page. It was actually really impressive. So I'm going to share that page with you now. But obviously, I'm not just going to teach you one page. I'm going to give you an overview right here of the three synthetic techniques that you need to know, okay, for this chapter. And then we're going to practice it a whole lot. I'm going to give you guys lots of practice problems and lots of application, okay? So let's go ahead and get started. I'm going to teach you guys the 3 important rules for synthesis that you need to know. The first rule, and so I'm calling this the synthetic cheat sheet. Like I said, you use this as your reference point for the whole chapter, okay? So the first thing is alkane halogenation. A lot of you guys already know this, but alkanes are unreactive. So if I want a functional group on an alkane, I'm going to need to halogenate it first. Do you guys remember what we used to halogenate alkanes? Radical reactions, right? So I could use something like Br2 over heat, okay? That would be an example of selectively halogenating an alkane so that I can then functionalize it later. So that's already functional. This is. But check it out. I could now do a bunch of stuff to it. I could substitute for that. I could do like an SN2. I could eliminate. I could do an addition reaction. Now this is kind of like, I just drew it like this because it kind of looks pretty, but this is kind of like not true. What you would do first is you would actually eliminate first and then you would add, right? Because addition reactions happen to double bonds, okay? So whatever, but I'm just saying that forming that first halogen is always going to be the first step anytime you start off with a simple alkane. So if you're starting off with just cyclopentane, you know, whatever you need, you're going to need to halogenate first, all right? So that's the first rule. Easy, right? Cool. Let's go on to the second rule. The second rule is called organometal alkylation. Now, 2 important words. What is organometal and what is alkylation? Well, organometal just stands for it's just any molecule that is part carbon and then part some metal, and they're bonded together, okay? So an example of that you're very familiar with is a sodium alkanide, okay? A sodium alkanide would be an organometal because I have a carbon with a negative charge, right? And then I have a sodium with a positive charge. See how well, in this case, I didn't draw them bonded together, but they're associated with each other. So that's an example of an organometal. Cool? Well, there's other types of organometals too. There's also this one right here that you don't know very well, but that's a Grignard. Later on, we're going to use that, okay? But for right now, just keep in mind that both of these count as organometals. And organometals are very strong nucleophiles because they create negative charges on carbon, okay? Well, it turns out that if you're ever trying to do a synthesis and you're trying to add carbons to a chain, let's say you start off with a 4-carbon chain and you need a 5-carbon chain, okay? Or you need a 10-carbon chain. What are you going to do? The only way that we can add carbon-carbon bonds in Organic Chemistry 1 is through organometal alkylation. That means reacting these with something that's going to add alkyl groups with an electrophile. So what electrophiles do we have? Well, we have 2 common electrophiles, but one of them we're going to use a whole lot more in this chapter, and that's alkyl halides, okay? Because remember that alkyl halides do the opposite. Instead of putting a negative on the carbon, they put a partial positive on the carbon. So that's perfect, because then what that means is the negative for one carbon is going to be attracted to the positive from another carbon, and they're going to link up. And that's what we call an alkylation. All right? Pretty easy. It's just whatever that alkyl group is, it gets added on. The X leaves as a leaving group. It turns out that a carbonyl is also a very common electrophile because it has a strong dipole pulling away from that carbon, so it also places a very strong partial positive on this carbon. Now, we're not going to deal with this one a whole lot in this chapter, but I still want you guys to hold on to this and realize that there's more than one nucleophile, there's more than one electrophile. All of these are the big 4. These big 4 are really important when it comes to making carbon-carbon bonds, all right? The ones we're going to deal with mostly today are the sodium alkanides and the alkyl halides, all right, which you already should have experience with. So that wasn't so bad, right? That's another very important rule. Anytime you're adding carbon, think sodium alkanide, think organometal, all right? So then what's the last thing? The last thing is probably the most useful of the 3, okay? And what it is that moving functionality, okay? There are many, many times in organic chemistry that I have a functional group in one place and I'm trying to get a functional group in a different place. I'm trying to go from one place to another. It doesn't even have to be the same group. It could be an alcohol here, and it could be a sulfur over here, whatever. The main point is that if you're trying to move one functional group from one place to another, then there's really only one way to do that. And that's by doing alternating elimination and addition reactions, okay? So elimination and addition, as you guys know, are opposites of each other, okay? So they're opposites. Since they're opposites, that means that they can kind of undo each other's effects, okay? So basically what we do is we eliminate to make a double bond, and that double bond will link two carbons together, and then we add to the carbon that we want to go in that direction. And then we do it again. Then we add to that carbon, then we eliminate, then we can do it again. And by doing successive elimination, addition, you can wind up moving the functional group from one part of the molecule to the other. And we're going to do a lot of this today. But I just want to let you guys know that's really the only way to move functional groups. If you want to take a functional group from the right side and make it to the left side, you have to do alternating elimination addition, okay? Well, it turns out that anytime you're eliminating and anytime you're adding, you actually have a choice of which direction to go in, because now you guys know how to do eliminations towards more substituted and less substituted, and you also know how to do additions towards more substituted and less substituted. The thing is, they had different rules. They had different names. So remember that if you're eliminating and it's towards the more substituted location, that was called Zaitsev, okay? But remember when you're adding and you're adding towards the more substituted, that's called Markovnikov, okay? That's really important that you link those two together, because both of those, the Zaitsev elimination along with the Markovnikov addition, are always going to go towards or move towards my more substituted locations, okay? So what that means is that if I can use reagents that are going to do Zaitsev eliminations and Markovnikov additions, I'm going to progressively move more towards the center of my molecule, the thing that's the most substituted. Does that make sense? Whereas I have opposites of that. I have, if I want to go towards the less substituted elimination, I would do a Hofmann, right? That's the less substituted. And if I want to move away from the center of the molecule to the less substituted addition, I would say it would be an anti-Markovnikov addition. Does that make sense? So both of these you put together because both of these are going to favor the less substituted direction, okay? And these are going to favor the outside of the molecule. So I'm just going to put here the outside of the molecule, and this one's going to favor the center of the molecule. Does that make sense? So what's so cool about this is that now it's almost like I've given you guys two roads, and you can choose which road to take based on what you're given. If you know you have to move, if you have a substituent that's all the way at the edge of the molecule and you need to move it towards the center, then we're going to start using a combination of addition and elimination of Markovnikov and Zaitsev. Obviously, the opposite would be true if we're trying to move towards the edges. Okay? Well, now all we need to do is you just need to figure out what are the actual reagents that we can use to do this. Okay? And let's start off with the eliminations first, because those are the easy ones. Okay? If I want to just do a Zaitsev elimination, what kind of reagents favor a Zaitsev elimination? Do you guys remember? Okay, so in general, I'm just going to put here a small, strong base. Okay? Small, strong bases favor Zaitsev. And really, just examples, you can think of your own, but why don't you guys just start yelling out some examples of small, strong bases? Yeah, I think that you got that one. It would be like, for example, NaNH2 is an example of a strong, small base, okay? Also NaH, okay? Also, any of the oxides, okay? So any OR negative would be a small, strong base. Of course, not if you make the R group too big, but if you keep it small, that would be a small, strong base, all right? And we can keep thinking of a few more. Well, even alkanides, okay? Alkanides are small, strong bases. In the right situations, they can favor that as well, okay? So these are all examples of bases that favor the that favor the Zaitsev elimination, so they're going to make the double bonds go towards the center of the molecule or towards the more substituted location, okay? Now, if I want to do a Hofmann elimination instead, then what kind of reagents would I use? I would use my bulky bases, right? And remember, there were just a few bulky bases that you needed to know. And I told you guys, like, LDA, T-butoxide, and LITMP. These are the really common ones, okay? That you just need to be aware of. If it's not one of these, then you can pretty much assume that it's not bulky. Okay? Cool. So now you guys already knew this, but now this is just helping you guys to solidify, okay, if I want to eliminate in the more substituted direction, I do Zaitsev. Less substitute, I do Hoffman. Now for additions, it turns out that addition is a lot more varied, because elimination, you just make a double bond, that's it. But for addition, you can either add alcohols, or you can add alkyl halides. Obviously, there's other things we can do too, but these are going to be the two most common categories, because a lot of times either an alkyl halide can be substituted for anything. You can just do an SN2 on it. And an alcohol tends to be a very common reagent that we like to add to stuff. So it's just important to know the alcohol reagents, okay? So let's go ahead and write down these reactions. What if I'm trying to do a Markovnikov addition of alcohol? So now this is at the point where I'm starting with a double bond. I'm trying to do a Markovnikov addition of alcohol. What reagents could we use for that? This is going to help you categorize all the reagents, okay? Well, the reagents we could use would be, first of all, the easiest one would be just acid catalyzed hydration, right? H2SO4 over H2O, okay? Or any HA, any strong acid. So we know that that would work. Are there any other reagents that make a Markovnikov addition of alcohol? Oxymerc, okay? This one's going to be a little bit bigger, but it's HgOAC2 with water, and then over NaBH4 and OH minus. Cool? So those are your two choices. I'm just going to kind of make a line there so you guys know that those are two different things. But those are our possibilities for Markovnikov addition. Why would I choose one over the other? Do you guys remember? What's better about one, or why? I don't know. What's a situation that I would want to choose, let's say, acid catalyzed hydration? Why would I want to choose that? If I want a shift. If I want a carbocation shift, you can even write here positive. So you just remember that would shift. Whereas oxymerc would never shift. So if you wanted a shift, that's not a good choice. Okay? Cool. So how could I do a Markovnikov addition of an alkyl halide instead? This one's really easy. Think about it. Markovnikov alkyl halide. I'm adding to a double bond. Just HX. Okay? HX is always going to do your Markovnikov addition of a halogen, and it will rearrange. And there's no equivalent of oxymerc for HX. There's no HX that won't rearrange. So just got to deal with it. Okay? So that's if I'm trying to add substituents towards the more center of the molecule. But what if I'm trying to go towards the outside with my addition reactions? How about if I'm trying to add an anti-Markovnikov alcohol or an anti-Markovnikov halogen? Well, in that case, we would use completely different reagents. So what we would use here for alcohol, do you remember a way to make anti-Markovnikov alcohol? Yes, you do, because you remember it's my favorite reaction. So it would be hydroboration. It would be BH3 THF over H2O2 and NaOH. Okay? So hydroboration is the way that we would add an anti-Markovnikov alcohol. Okay? What's the way that we wanted to, if we wanted to make an anti-Markovnikov halogen instead? Not alcohol, halogen. Well, then we could use a radical reaction, because remember that HX is going to go Markovnikov unless we add peroxides. Okay? If we add peroxides, then that makes it anti-Markovnikov instead. Now, maybe it's making sense to you why I kept emphasizing, guys, remember hydroboration and remember radical hydrohalogenation. Because I kept saying this is going to be very important for synthesis. Why? These are the only two reactions in Orgo 1 that go anti-Markovnikov. So these are going to be the only two addition methods that you have to go outside towards the peripheral. Okay, towards the edges of the molecule. That's why it's really important. Okay? So what's so cool about this chart is that, yeah, a bunch of reagents aren't here. Okay, I totally get that. But the important reagents for moving functional groups are here now. So what that means is that now, as we're moving functional groups from one place to another, we can just use this as a cheat sheet and say, which direction do we need to go? Is it more substituted or less? And then you figure out what to do. Now, also you might be wondering, okay, Johnny, how do I know when to add? How do I know when to eliminate? Okay? It's just whatever you're starting with. So if you start off with a double bond, let's say the question is, turn this double bond into this functional group. Oh, on the other side of the molecule. Well then, if you're starting with a double bond, your first step always has to be an addition. Okay? So that means you would look towards the addition section and you'd say, okay, is this going to be a more substituted direction or less? That's the one you pick. Okay? Then opposite's true. If you start off with an alkyl halide or an alcohol, then you need to start moving it somehow, so you need to eliminate first. And then once again, you would look at your chart and say, okay, is it going to be eliminating in the more substituted or the less substituted? It's really awesome how it really turns into like a formula once you have this in your mind. You start to think, oh, what can I do? What do I need to do? Instead of it just being a guessing game. Now you actually have a blueprint for what to do. Okay? So that was a really big intro of this sheet. Like I said, this basically summarizes the whole chapter. Now what we're going to do is you're going to do a lot of practice, and I'm going to individually focus on each of these sections. All right? So I hope that made sense. Let me know. But also just wait it out a little bit in case you're confused, because I'm going to go into depth on all three of these things. We're going to do a lot of examples. All right? So let's go ahead and move on.